Okay, so welcome back to another video. So in today's video we have a little number theory problem, and it says find all n that are actually positive integers such that n to the fourth power plus 4 is prime. Okay, so there's going to be a little identity we're going to use. This is actually known as the Sophie Germain's identity, which I will write this down first. Sophie Germain identity, and that states as the following formula, like so, and that says x to the power 4 plus 4 times y to the power 4th is equal to the following expansion. It says that this is equal to x squared plus 2y squared plus 2xy, and then we multiplied this by x squared plus 2y squared, and then subtract 2xy. And so this identity over here is well known, especially for in math contest problems, especially like math Olympiads use this technique. And Sophie Germain actually was a French mathematician from 1776 to 1831. So her contributions in work can include stuff with acoustics, elasticity, and early number theory as well. Interestingly, she actually she wrote to Gauss outlining her strategy for finding a general solution to Fermat's last theorem, which it's a very well known theorem in the world of number theory or in just math in general. You can look that up yourself if you want to for the more information on that. But we're going to actually use this identity to actually prove the following. Find the solutions for n, some positive integers n. But before I get into that, let's actually do a little derivation on how we get this formula over here. So let's actually just jump right in. Okay, so if I start with the left-hand side of the equation, so let's say if I can just write this as, so I can write this as x to the 4 plus 4y to the 4. And then I'm actually going to add and subtract a 4x squared times y squared. So 4x squared, then y squared. Okay, now what you notice is that these three terms, I can actually put this together into a double binomial factor. So that actually comes down as x squared plus 2y squared, then quantity squared. And then I can actually, and then this can be factored out as 2xy quantity square, like so. What's really neat is that if we use the difference of squares formula, so we all know difference of squares, that says that, right over here, that says that a squared minus b squared is actually just equal to a plus b then times a minus b. I'll just write diff of squares. So if I were to set this quantity expression as a and set this quantity expression as b, and then just write the following formula given how difference of squares are defined as, then we actually get the following expression. We would get that this is just equal to, so if I just plug in a, so that means we have x squared plus 2y squared, then add this with 2xy, then we multiply this, do the same thing just like so, but except it includes it's the subtraction. X squared plus 2y squared, then subtract 2xy, and then there's the proof complete like so. But we want to show the right hand expression. So there we have it. So we have the left hand is equal to the right hand, which is just the same as this one, like so. So now we solved that direct verification. Now let's actually just jump into finding the solutions. Okay, so now we can write n to the power 4 plus 4. We're just gonna start finding the solutions. So if we use Sophie Germain's identity, and if we just plug in our inputs, so we say x is equal to n, and then y is equal to 1, then we just plug in the following generalization into over here, like this identity over here, like so. And then we would have the following is that n squared plus 2, then subtract, or I guess plus, whichever way you want to put it, plus 2n, then times n squared plus 2, then subtract 2n is equal to n to the power 4 plus 4. Okay, so we want to find a solution for n positive integers n such that n to the power 4 plus 4 is prime. So if that's the case, if saying that n to the power 4 plus 4 is prime, then that gives us the idea that either n squared plus 2n plus 2n is equal to 1. So I'll write it like this. Either n squared plus 2 plus 2n is equal to 1, or n squared plus 2 minus 2n is equal to 1. Okay, so we have to figure this out. So as you notice that if I were to solve the solutions, which you can see that, so if I just subtract 1 to both, so we have n squared plus 2n, I'll just write this in front of the constant. So plus 1 equals 0, and then the next one below you do the same thing, so n squared minus 2n, then subtract 1, so that means plus 1 is equal to 0. Notice that for this one, let's see, I'll just write this again for a second time, plus 1, then you'll notice that you can actually just factor this, unfoil this, and you'll get that this is just n plus 1 times n plus 1 squared equals 0, and you see that n is equal to -1. However, -1 is a negative number which is not part of the set of positive integers, so we can just exclude this solution. So really, this has to imply that n squared minus 2n plus 1 is equals 0, that this actually has a solution that satisfies the following. But let's actually just verify this ourselves just to see. N squared minus 2n, then plus 1. Then if I factor this, then let's see, you can actually factor this out again. So this will be n minus 1 squared equals 0, but then n is equal to 1. Now notice that if I plug n back to the solution, so n to the power 4 plus 4, just plug in 1 to the power 4 plus 4 is equal to 5. And guess what? 5 is a prime number. So the only solution is that n is equal to 1, such that it satisfies that n to the power 4 plus 4 is prime. So there we have it. The only solution is, the only positive integer that satisfies the following is that n equals 1, like so. So there we have it. So yeah, that's pretty cool if you ask me.